Good morning, everyone, and welcome to this Midwest DEWS research webinar. Thank you to everyone who has joined us today. We're really glad that you're here. So my name is Molly Wolleson, and I am the Regional Drought Information Coordinator with NIDIS, which is the National Integrated Drought Information System, and I coordinate our Midwest region. So I hope you're all safe at home during this winter storm. I'm here in Champaign, Illinois, and we've gotten quite a few inches of snow already. And I guess we're expected to get so much that I hear Ginger Z from the Good Morning America show was here to actually shoot live this morning. So quite a historic event. So let's switch gears though to drought. We have an exciting webinar today, and it's focused on showcasing results from a recent NIDIS-funded study looking at the characteristics and predictability of Midwest drought. Our speaker today is Dr. Andy Hoell, and he's with NOAA's Physical Sciences Laboratory, and he is the one leading this research. So this work was recently published in the Journal of Hydrometeorology, and a link to that study will be put in the chat box here in just a few minutes. We will have a Q&A session following the presentation, and we really would like to provide an opportunity for you to provide feedback on the plans for the future analysis with this project. So this webinar is being recorded, and we will post it on drought.gov and our YouTube channel a few days after this webinar concludes. Before I turn it over to Andy, I did want to just briefly provide a little bit of information on NIDIS and the Midwest DEWS. So NIDIS, the National Integrated Drought Information System, was originally mandated by Congress in 2006, and our goal is to proactively manage drought-related risks and to help our country become more prepared for drought. So NIDIS is building this foundation for a national drought early warning system, or DEWS, through the development of regional DEWS. And as I mentioned previously, this region is called the Midwest Drought Early Warning System, or DEWS. And really what's unique about this is the network of partners and stakeholders that share information to help us cope with the impacts of drought. The ultimate goal of NIDIS is to create a national drought early warning system. And each DEWS has similar components, but really there is a regional flavor reflecting the needs of each region. So the Midwest DEWS was officially launched in early 2016, and our newly released strategic action plan is available on drought.gov, and I will also put a link to that in the chat box here in just a little bit. So just a little bit more about our regional drought early warning systems. DEWS utilizes new and existing partner networks to really help us optimize the expertise that we have in the region across federal, state, local, and academic partners. And the goal of a DEWS is to make climate and drought science easily understandable and usable for decision makers. And in the end, we really hope that we can better predict, better monitor, and overall decrease the impacts that we experience from drought. So now I would like to turn it over to Andy for the presentation. This presentation has been pre-recorded, and Andy is here to help us answer any questions that you might have. So feel free to go ahead and type in your questions as we go along, and we will address those that we weren't able to get to at the end, or those that require a little bit more discussion. So I am going to launch the recording here in just 1 second. It might take a minute as it processes.
Hello everyone, and thank you for joining today's webinar. I'm Andy Hoell from the NOAA Physical Sciences Laboratory, and I will present characteristics and predictability of Midwestern United States drought. I'd like to thank NIDIS for organizing today's webinar and for supporting the research that I will present. Today's presentation is based on an article by the same name that appeared in the November 2021 issue of the Journal of Hydrometeorology. I'd like to thank my co-authors of this article, Trent Ford of the University of Illinois, Molly Wolleson of NIDIS, Jason Otkin of the University of Wisconsin, and John Eischeid of the NOAA Physical Sciences Laboratory. We noted in the research literature that few studies generalize drought characteristics specifically in the Midwestern United States. Rather, studies focused on continental scale features spanning the United States and North America. We also noted that aspects of individual drought events were examined in some depth, but these studies lack the generality necessary to be applied to develop comprehensive drought early warning. Notable events affecting the Midwest, among other regions, that have gained considerable attention include events in the 1930s, the 1950s, and 2012. Therefore, the goal of this study was to build a more complete understanding of the characteristics and predictability of Midwest drought to equip forecasters and planners with the knowledge to better anticipate and prepare for future events. An outline of this presentation is as follows. In the first part, I will describe tools and methods used in this study. Of particular note are the land surface model simulations used and how they were used to create an integrated drought index. In the second part, I will describe local drought drivers, focusing on the contribution of soil moisture, runoff, and snow water equivalent, and how precipitation and temperature shape them. In the third part, I separate the Midwestern United States into 4 regions of coherent hydroclimatic variability and describe the characteristics of drought within them, including variability, onset, persistence, and demise. In the fourth part, I examine whether physical factors like El Niño Southern Oscillation and related atmospheric circulations are associated with drought, potentially rendering them more predictable. And finally, I will end with a summary of this work and introduce some topics for further drought study in the Midwestern United States. In the first part of the presentation, I will describe the methods and tools used in this study. The analysis period in this study spans 1916 to 2015. The study begins in 1916 because that's when the land surface model simulations, which we use to quantify drought, begin. The study ends in 2015 because that's when the 20th century reanalysis, which we use for the atmospheric circulation, ends. We use 4 land surface models from the UCLA Surface Water Monitor. The land surface models are analyzed monthly on the same fixed 0.5 by 0.5 degree latitude and longitude grid. That means the Earth is separated into rectangles that are 0.5 by 0.5 degrees in size. The 4 land surface models used are the Variable Infiltration Capacity Model version 4.0.6, the NOAA model version 2.7, the Sacramento SMA model, and the Catchment model. All 4 land surface models were forced by the same estimates of the time-varying meteorology. This includes daily precipitation, wind speed, average temperature, water vapor pressure, and downward solar and long-wave radiation. Our reasons for using these land surface models are twofold. First, century-long land surface model simulations allow us to better identify robust characteristics than if we were to use a shorter time period. Second, using 4 land surface models, as opposed to just 1, limits the effect of biases introduced by a single model. The atmospheric circulation is estimated using the 20th century reanalysis version 3. Specifically, we use 300 hectopascal winds, which are about 30,000 feet above sea level. Sea surface temperatures are from the extended reconstructed sea surface temperature dataset version 5. Drought, or hydroclimate more generally, is measured in this study using an integrated drought index, or IDI, derived from the 4 land surface model simulations. Our integrated drought index was designed to include facets of drought that are important to the Midwest: agricultural drought, snow drought, and hydrological drought. Here, agricultural drought is measured by total column soil moisture, snow drought is measured by snow water equivalent, and hydrological drought is measured by runoff. The integrated drought index used in this study follows Moen-Lettenmeyer in 2018. This integrated drought index is based on 3-month runoff and total moisture storage, which itself is defined as the sum of total column soil moisture and snow water equivalent. It's important to note that an integrated drought index can be constructed using different hydroclimatic variables relevant to a given region. For example, a recent study that focused on India constructed an integrated drought index based on precipitation, soil moisture, and runoff. The integrated drought index was created using a 3-step process. First, monthly total moisture storage, the sum of total column soil moisture and snow water equivalent, was standardized in each of the 4 land surface model simulations. Second, 3-month runoff was standardized from each of the 4 land surface model simulations. And finally, the 4 standardized total moisture storage and 4 standardized 3-month runoff indices were averaged to create this integrated drought index. Quantities were standardized as follows. Quantities were fitted to a gamma distribution, followed by a transformation to a normal distribution with a mean of 0 and a unit variance. A 1916 to 2015 monthly reference was used. Here I illustrate how the Integrated Drought Index recreates historical hydroclimate using the 2012 calendar year as an example. Note that our definition of the Midwestern United States spans 13 states, and these states are outlined in dark black lines. The states included are North Dakota, South Dakota, Nebraska, Kansas, Missouri, Iowa, Minnesota, Wisconsin, Michigan, Illinois, Indiana, Ohio, and Kentucky. 2012 began with drought in the upper Midwest and wet conditions in the lower Midwest. From January to February 2012, little change was indicated by the Integrated Drought Index. In March 2012, the upper Midwest and the plains fell deeper into drought. And from March to April 2012, the lower Midwest fell into drought as well. By May 2012, the lower Midwest fell deeper into drought, and drought emerged rather quickly in the central Great Plains. And the deepening of drought over the central plains and lower Midwest continued in June. Drought further deepened over the Midwest United States in July 2012, with the exception of an area in central Minnesota. While there was some relief in August 2012 in the Midwestern United States, that relief was tempered as drought remained across the region. September 2012 was a month of change, as the Integrated Drought Index moved closer to average in the lower Midwest because of noteworthy precipitation, while the Integrated Drought Index plunged to very low values as drought built quickly in the northern plains and upper Midwest. In October 2012, and for the remainder of the calendar year, drought remained in the Great Plains and upper Midwest. Next, I will present the drivers of the Integrated Drought Index and thus hydroclimatic variability in the Midwestern United States. The Integrated Drought Index was constructed using soil moisture, snow water equivalent, and runoff. In the next 3 slides, I will show how each of these land surface quantities shape the Integrated Drought Index in the Midwestern United States. This analysis is performed by calculating the monthly correlations between the Integrated Drought Index and soil moisture, snow water equivalent, and runoff, and grouping them by 3-month seasons: December to February, March to May, June to August, and September to November. The deeper blues indicate the strongest correlations, which suggest a strong causal link. On this slide, soil moisture is shown to be a key contributor to the Integrated Drought Index in all seasons. During June to August, summer, and September to November, fall, soil moisture and the Integrated Drought Index are almost perfectly correlated. Soil moisture is also strongly correlated with the Integrated Drought Index in December to February, winter, and March to May, spring. While soil moisture and the Integrated Drought Index are nearly perfectly correlated in the Central Plains, the correlations are lower in areas where the ground freezes and can be covered by snow, namely the Northern Plains and the Great Lakes region. On this slide, the correlation between snow water equivalent and the Integrated Drought Index is shown. We find that snow water equivalent only modestly contributes to the Integrated Drought Index variability in December to February and March to May, the times of the year when snow often falls and accumulates in the region. However, the correlations reach a maximum of about 0.5 in the upper Midwest and Great Lakes region, which is much smaller than the correlation between the Integrated Drought Index and soil moisture shown in the previous slide. This indicates that snow water equivalent plays a secondary role in modulating drought even in the cold season. On this slide, 3-month runoff is shown to be a key contributor to the Integrated Drought Index in all seasons. During June to August and September to November, 3-month runoff and the Integrated Drought Index are almost perfectly correlated. 3-month runoff is also strongly correlated with the Integrated Drought Index in December to February and March to May. Correlations between the Integrated Drought Index and 3-month runoff and the correlation between the Integrated Drought Index and soil moisture share similar pattern and magnitude, indicating similar contributions to the hydroclimatic variability in the region. This is not a big surprise, since previous research has shown that 3-month runoff and soil moisture vary similarly. We now turn our attention to probing variables related to the Integrated Drought Index variability that are forecast on an operational basis at the weather to subseasonal to seasonal timescales. Namely, we focus on precipitation and 2-meter temperature to provide further insights into our predictive understanding of Midwest drought. We adopt the same perspective as we did previously. That is, we calculate the monthly correlations between the integrated drought index and precipitation and 2-meter temperature and group them by 3-month season: December to February, March to May, June to August, and September to November. In the case of precipitation on this slide, the deepest greens indicate the strongest positive correlations, which suggests a strong causal link. Gray indicates no significant relationship. Precipitation is found to be the principal driver of the integrated drought index, given positive correlations between 0.4 and 0.6 across the region during most seasons. These generalizations hold especially true in the warm season of June to August and September to November, shown in the bottom 2 images. However, the precipitation and integrated drought index relationship is a more nuanced approach during the cold season. During December to February, no significant correlations are found in the northern plains and into the Great Lakes region of the Midwest. We hypothesize that precipitation and the integrated drought index are not closely related because December to February is the dry season, which we will show shortly, and that land surface tends to be frozen this time of year. During March to May, lower precipitation and integrated drought index correlations are found in parts of the Great Lakes region of the Midwest, perhaps because of the reason we outlined for December to February in the northern Great Plains region. By contrast, the same perspective, but relating 2-meter temperature in the integrated drought index, reveals that temperature only plays a modest role in modulating hydroclimate during summer over the Central Plains. That is, temperature in the integrated drought index are inversely correlated, such that higher temperatures lead to a lower integrated drought index and vice versa. This is shown in the red shading in the lower left-hand panel for June to August. Otherwise, no significant correlations between temperature and the integrated drought index are found in the other seasons and areas of the Midwestern United States. These results indicate the primacy of precipitation in driving hydroclimate, and thus drought on monthly timescales during the seasons in the Midwestern United States compared to temperature. Next, I present regional drought characteristics in the Midwestern United States. We begin with an analysis of precipitation to establish a baseline from which to probe drought characteristics across the Midwest. This analysis indicates that precipitation characteristics are quite different from one area to the next. Shown on the left-hand map is calendar year average precipitation. Shown in the right-hand time series are box plots of monthly precipitation for 1916 to 2015. The calendar year average precipitation map on the left shows a strong gradient in precipitation that is observed along a west to east oriented axis extending from the northern Great Plains to the Ohio River Valley. Areas in Ohio, Indiana, Illinois, and Missouri on average receive in excess of 1,000 millimeters of precipitation each year, while areas in the Dakotas, Nebraska, and Kansas receive between 500 and 700 millimeters. Calendar year average precipitation totals are related to differences in the precipitation seasonal cycle across the Midwest. This is indicated by the box plots of monthly precipitation at 4 locations: Bismarck, North Dakota, Milwaukee, Wisconsin, Lincoln, Nebraska, and Columbus, Ohio. Areas with a shorter wet season observe less annual precipitation than areas where precipitation is more evenly distributed across the calendar year. The western and northwestern areas of the Midwest, as represented by Bismarck, experience a single wet season spanning May to September, reaching a maximum in June. A transition to less pronounced, shorter, dry seasons occurs as one moves south and east. Columbus, Ohio, representing southeastern areas of the Midwest, do not have a pronounced wet and dry season. Even though the largest monthly precipitation totals in Columbus occur on average in spring and summer, appreciable precipitation is still observed in fall and winter. Motivated by differences in precipitation across the Midwest, we assess the spatial scales of drought variability in the region by examining integrated drought index correlations between 4 points: Bismarck, North Dakota, Milwaukee, Wisconsin, Lincoln, Nebraska, and Columbus, Ohio, and the rest of the region. Based on this analysis, we find that droughts tend to occur at local to regional scales. The correlations show that drought is related to a small area surrounding each location, and that drought variability can be dissimilar even for nearby locations like Bismarck and Milwaukee. For example, hydroclimate in Bismarck is principally related to hydroclimates in North Dakota, South Dakota, and Minnesota, while hydroclimate in Columbus is principally related to hydroclimates in Ohio, Kentucky, and Indiana. Given the large spatial variations in hydroclimate in the Midwestern United States, A hierarchical clustering algorithm based on Ward's method was applied to the monthly integrated drought index to identify regions of coherent hydroclimatic variability. Ward's method identifies areas in which the variations of the integrated drought index are most closely related. Though we could select as many clusters as there are points from the land surface models in the Midwest, we select 4 of them to balance our desire to generalize drought behaviors in the Midwest and to identify regions that are representative of the integrated drought index variability of the grid boxes that make up the region. The 4 identified clusters shown in the left-hand image span approximately the quadrants of the Midwest: the Northern Great Plains shown in orange, the Great Lakes shown in pink, the Central Great Plains shown in blue, and the Ohio Valley shown in green. In the 4 maps on the right, we test whether 4 regions identified by the hierarchical clustering algorithm can adequately capture the hydroclimatic variability within them. We do so by correlating the area average integrated drought index of all grid points within the region to each grid box in the Midwestern United States. We find that greater than 3/4 of the grid points in each region are correlated with the region average at more than 0.7. These correlations suggest that these 4 regions are appropriate separations of the Midwestern United States from which to study hydroclimate in the region. Based on the regions of coherent hydroclimatic variability identified in the prior slide, we now focus on the time series of area average integrated drought index to examine the intricacies of hydroclimate within each region. The images on the slide show the monthly integrated drought index in orange bars and the 12-month running average integrated drought index in the solid black line for each of the 4 regions: the Northern Great Plains, the Great Lakes, the Central Great Plains, and the Ohio Valley, all during 1916 to 2015. The time series illustrate intricacies of regional drought within the Midwestern United States and highlights considerable hydroclimatic differences between each region. Though annual droughts are a feature in all 4 regions, the variability of the integrated drought index, persistence, clustering of low and high index values in the same decade, and multi-decadal variability of the integrated drought index are largely different. Nonetheless, there are 7 epochs in which all 4 regions experience low integrated drought index values simultaneously. These epochs include 1917 to 1918, 1925, 1933 and 1934, 1939 and 1940, 1963 and 1964, 1988, and 2012. One common feature among the regions is what appears to be an increasing trend in the integrated drought index from early in the study period to later in the study period. This suggests a decrease in the prevalence of drought during the 20th and 21st centuries. While this trend appears in all regions, it is especially pronounced in the Northern and Central Great Plains. We will further examine this apparent trend later in the presentation. I will now describe salient features of the integrated drought index variability in each of the 4 regions. In the Northern Great Plains shown in the top row, aside from semi-regular annual hydroclimatic variability between 1940 and 1970, the Dust Bowl spanning 1934 to 1931, and the wet epoch spanning the 1980s, 1990s, and early 2010s stand out as the most prominent features in the integrated drought index time series. Other noteworthy droughts in the Northern Great Plains include 1958 to 1963 and the late 1980s and 2012. Despite its proximity to the Northern Great Plains, the Great Lakes, shown in the second time series from the top, experienced rather different hydroclimatic variability during 1916 to 2015, further highlighting the value of separating the Midwest into smaller regions for the purpose of studying drought. Not only was the timing of positive and negative regional integrated drought index values different between the Northern Great Plains and the Great Lakes, the persistence of such values differed as well. By this metric, the Great Lakes region did not experience the Dust Bowl with such vigor. In fact, drought was only felt in 1931 and 1933. The epoch in which drought was most prevalent spanned the mid to late 1950s, and even during that time there were indications of brief drought relief, as the integrated drought index approached and even exceeded 0. Other noteworthy droughts in the Great Lakes region occurred during the mid-1960s and 1977. Regional average integrated drought index variability over the Central Great Plains, shown in the second time series from the bottom, shares considerable commonality with the Northern Great Plains, owing to their geographical location and similarities in their hydroclimates as indicated by the precipitation annual cycle. The Dust Bowl stands out prominently in the integrated drought index time series spanning the 1930s and early 1940s. The region also experienced a significant prolonged drought spanning 1952 to 1957. Though single-year droughts have occurred since 1980, for example 1981, 1988, 2000, and 2012, the integrated drought index was predominantly above average, and considerably so, after 1980. Ohio Valley hydroclimate, shown in the lower panel, had the least in common with the other regions in the Midwest during 1916 to 2015. Not only was the timing of above and below average integrated drought index values different from the other regions, the variability of the integrated drought index was considerably larger than each of the other regions as well. The 1930s and early 1940s were generally a dry time in the Ohio Valley, as indicated by annual droughts in 1931, 1934, and 1941. However, between those droughts, above average integrated drought index conditions occurred, which sets this region apart from each of the others. Like the Central Great Plains and Great Lakes, the mid-1950s and mid-1960s were also a dry time in the region. Since 1970, there have been few single-year droughts, namely 1977, 1988, 2000, and 2012, but otherwise a wetter climate relative to the past prevailed, as the 1970s, 1990s, and 2000s saw persistently high integrated drought index values. A key consideration of drought in the Midwestern United States is how quickly they can emerge or intensify, an event known as flash drought. Noted in the time series of the integrated drought index are rapid changes in hydroclimate from one month to the next. So we examine these changes in more detail, though we note that monthly differences in the integrated drought index may not be ideal for quantifying flash drought because those droughts may develop in just a few weeks. The monthly hydroclimatic variability in each region, the Northern Great Plains, the Great Lakes, the Central Great Plains, and the Ohio Valley, are shown by histograms of monthly changes in the integrated drought index. The histograms for all regions indicate that the most likely month-over-month changes in integrated drought index are near zero, as expected. However, the frequency of large changes vary by region. Focusing on the Ohio Valley, its histogram of month-to-month integrated drought index changes is flatter than the other three regions, which indicates there is a higher likelihood of large month-over-month hydroclimatic changes. And indeed, we see that the integrated drought index changes of greater than 1 and less than -1 occur about 3% of the time, which is much larger than each of the other three regions. Though it is not shown here for brevity, there is a seasonality and regionality to the magnitude of month-to-month integrated drought index changes. September to November and June to August stand out as the seasons in which the largest changes in the integrated drought index occur, then followed by March to May. Large positive changes during these seasons are related to abundant precipitation that can fall, while large negative changes during these seasons are related to the lack of precipitation and considerable evapotranspiration that can occur during the warm seasons. The smallest changes in the integrated drought index occur in December to February, over all regions except the Ohio Valley, likely a result of being cold and/or dry season in the other three regions. In the Ohio Valley, larger changes in the integrated drought index in December to February are possible because appreciable precipitation is still observed this time of year and the ground may not be frozen throughout. I will now present characteristics of regional droughts in the Midwest during 1916 to 2015 based on a collection of events identified using the method of MOE 2011, whereby droughts begin when the regional average integrated drought index falls below -0.8 and persist until the regional average integrated drought index exceeds -0.2 to ensure complete recovery. The image on this slide shows the likelihood of drought persisting for a given length of time in each of the four regions. The Northern Great Plains is shown in orange, the Great Lakes is shown in pink, the Central Great Plains is shown in blue, and the Ohio Valley is shown in green. The frequency of drought persistence in each of the four Midwestern United States regions illustrates that the likelihood of drought duration depends on location. Droughts last considerably longer in the Great Plains regions than they do in the Great Lakes or Ohio Valley regions. The likelihood of drought lasting at least 1 month in each region based on the drought definition we adopted is approximately 20 to 22%, which is generally consistent with the drought definition used by the U.S. Drought Monitor. An e-folding decay in the frequency of drought as a function of persistence is noted for each region, though the magnitude of the decay varies from one region to the next. For example, the Northern Great Plains was 4 times more likely to experience a drought lasting at least 12 months than the Ohio Valley. This is consistent with the larger magnitude of the serial correlation of the local integrated drought index, which is linked to the climatological precipitation seasonal cycle, in which much of the Northern Great Plains experiences a single wet season, while the Ohio Valley receives precipitation during all calendar months. The seasonality of drought onset and recovery in each of the four Midwestern United States regions is illustrated on this slide based on the collection of events we identified. For each season, December to February, March to May, June to August, and September to November, the frequency of onset in brown and recovery in green is shown. Based on our definition, each region has a preferred season of drought onset and recovery, and these preferred seasons generally follow the precipitation seasonal cycle, whereby droughts tend to begin and end during wet seasons, and particularly during times in those wet seasons when the precipitation variability relative to the median is either largest or smallest. For the northern Great Plains, droughts overwhelmingly begin and end outside of winter, which on average is the dry time of year. Drought onset is most likely to occur in September to November and March to May, the times of year in which precipitation variability is largest compared to the median, with a dip in the frequency of onset in June to August, the wettest 3-month season, with relatively low precipitation variability. Drought demise is most likely to occur during the wetter seasons, and in particular during June to August and September to November. The frequency of drought onset and demise in the central Great Plains is quite similar to that of the northern Great Plains. This is not surprising given the similarities between the two hydroclimates. Drought onset and demise in the Great Lakes and Ohio Valley regions of the Midwest occur more equitably across the seasons than is observed over the Great Plains regions. For the Great Lakes region, drought onset and demise occur nearly as frequently in December to February, March to May, and June to August, but increase greatly in September to November. The higher frequency of onset and demise in September to November relative to the other seasons can be attributed to the precipitation seasonal cycle, which is quite variable relative to the mean during this season. For the Ohio Valley region, owing to a relatively flat precipitation seasonal cycle, little difference is found in the frequency of drought onset and demise across the seasons. However, there are slight increases in March to May and September to November. March to May is the wettest 3-month season, and there is considerable precipitation variability, while September to November is the driest of the 3-month seasons, which too experiences considerable precipitation variability relative to the other seasons. Noted in the Integrated Drought Index time series for each of the 4 focus regions in the Midwestern United States was an increasing trend in this index. Also noted was an abundance of regional droughts in the 1930s and 1950s, and the relative scarcity of regional droughts after the 1990s. This motivated us to probe decadal drought occurrence across the Midwest, shown in the images on this slide, as measured by the fraction of time spent below -0.8 standardized departures of the Integrated Drought Index for each of these 9 decades. Indicated hereby are notable decadal variations in drought prevalence over the Midwest, and that the drought prevalent decades generally occurred early in our period of record. Drought was especially prevalent in the 1930s and 1950s, as large portions of the Midwest experienced an integrated drought index of less than -0.8, approximately 2 to 4 times as often as during the 1990s and 2000s. On this slide, we compare precipitation in a recent 30-year period, 1980 to 2009, to precipitation in a past 60-year period, 1920 to 1970, to test whether precipitation changes are related to the decrease in drought prevalence over the Midwestern United States. Shown here is the precipitation percent difference in shading, with stippling indicating precipitation differences that are statistically significant at the 95% confidence level. We find that the Midwest was much wetter in the recent 30-year period compared to the prior 60-year period, which explains the decrease in drought prevalence during that time. Increases in annual precipitation of up to 15% occurred in the climatologically driest areas of the Midwest, notably the Great Plains and the Upper Midwest. The climatologically wetter areas in the lower Midwest, Ohio Valley, and Great Lakes regions have experienced a more modest annual precipitation increase of up to 9%. In this section, I will present regional drought predictability in the Midwestern United States. Toward establishing a predictive understanding of the causes of Midwestern United States hydroclimatic variability, we relate monthly changes in regionally average integrated drought index to sea surface temperatures and 300 hectopascal meridional wind, or northward wind anomalies. Relationships with meridional wind anomalies help to diagnose how the atmospheric circulation shapes drought, while sea surface temperature anomalies, especially those over the Pacific Ocean, may serve as key sources of longer lead predictability for drought because of their slow variations and established effects on global climate. Since a key mode of Pacific sea surface temperature variability, the El Niño Southern Oscillation, is related to temperatures and precipitation over the United States, it is expected to play a role in hydroclimatic variability in at least some regions of the Midwest. These analyses were performed by calculating the linear regression between monthly changes in the Integrated Drought Index and sea surface temperatures and 300 hectopascal winds, and grouping them by 3-month seasons: December to February, March to May, June to August, and September to November. The deepest reds indicate the strongest positive regressions, and the deepest blues indicate the strongest negative regressions. The 4 maps on this slide show the regressions of monthly changes in the integrated drought index in the Ohio Valley onto the 300 hectopascal meridional wind anomalies grouped by season. These alternating areas of positive and negative meridional wind regressions indicate that hydroclimate in the Ohio Valley is related to atmospheric waves spanning the North Pacific Ocean and North America during all seasons. A unique feature gleaned from these regressions is that the size, origins, and locations of these waves depends on season. In December to February, it appears as though waves originate in the western tropical and subtropical Pacific Ocean, which suggests that processes in the tropics may be playing a role. Also during December to February, the waves are larger than during the other seasons and appear to arc northward over the Pacific Ocean into North America. In March to May, the regressions are weaker, which suggests that a few different phenomena may be at play, given that this is the wet season in the Ohio Valley. The waves are confined principally to the eastern North Pacific Ocean in North America, which suggests that processes more local to the Ohio Valley are driving hydroclimate there. In June to August, the regressions are very concentrated and aligned from west to east and span the North Pacific and the northern United States. And then finally, in September to November, the waves are aligned from west to east, but they are also larger and stronger than June to August. The 4 maps on this slide show the regression of monthly changes in the integrated drought index in the Ohio Valley onto sea surface temperature anomalies grouped by season. These regressions indicate few relationships between hydroclimate in the Ohio Valley and coherent sea surface temperature anomaly patterns representing predictable modes of climate variability. The El Niño Southern Oscillation is only related to the Ohio Valley hydroclimate in December to February, given the negative regressions over the tropical central and eastern Pacific Ocean. This means that La Niña is related to increases in the integrated drought index and El Niño is related to decreases in the integrated drought index. This wintertime relationship makes sense because precipitation in the Ohio Valley is generally below average during El Niño and above average during La Niña. Otherwise, Ohio Valley hydroclimate is not related to sea surface temperatures in March to May, and is only related to sea surface temperatures in the North Pacific in June to August and September to November. These results suggest that long lead predictability of drought in the Ohio Valley is limited outside of winter, since slow varying predictors in the climate system like sea surface temperatures do not apply. We now turn our attention to another region, the Northern Great Plains, and contrast it with the Ohio Valley. Shown in this slide are the regressions of monthly changes in the integrated drought index in the Northern Great Plains onto the 300 hectopascal meridional wind anomalies grouped by season. Again, we see alternating areas of positive and negative meridional wind regressions related to Northern Great Plains hydroclimate, which indicates the importance of atmospheric waves in shaping drought in the region. However, the characteristics of the waves related to Northern Great Plains hydroclimate are different from those related to Ohio Valley hydroclimate. During December to February, we see a weak and incoherent pattern of meridional winds related to Northern Great Plains drought. This is not too much of a surprise given that this is a dry season in the region and changes in the integrated drought index are not large during winter. During each of the other seasons, we see atmospheric waves oriented west to east that span the North Pacific and North America. The size of these waves and their exact positioning vary slightly from one season to the next. The central question is whether we could predict the atmospheric waves related to Northern Great Plains hydroclimatic variability months in advance based on slow varying behaviors in the climate system like sea surface temperatures. The answer to this question is unlikely, as we can see that the regressions of the monthly Northern Great Plains integrated drought index onto sea surface temperature anomalies grouped by 3-month seasons are incoherent and weak. This is especially true for phenomena like the El Niño Southern Oscillation, which are not prominently featured in these regression maps. I showed the Northern Great Plains here as an example. Similar results are found for the 2 other regions that we did not consider for brevity, the Central Great Plains and the Great Lakes regions. I will conclude with a summary and pose some questions for future drought study in the Midwestern United States. A key feature discussed in this study was the decreasing trend in drought prevalence in the 20th and 21st centuries in the Midwestern United States. 2 key questions follow. First, how likely was the observed decrease in drought frequency from 1916 to 2015? And second, is the decrease in drought frequency projected to continue in the 21st century, and if so, what would cause it? Also discussed were drought characteristics in the 4 Midwestern United States regions: the Northern Great Plains, the Central Great Plains, the Great Lakes region, and the Ohio Valley region, including the seasonality of onset and demise, as well as the likelihood of persistence, it is natural to ask, how are drought characteristics projected to change? We ended the presentation with some aspects of the climate system that are related to Midwestern United States hydroclimate, and whether they could be leveraged as predictors of drought in the region. From this, we ask, are aspects of drought projected to become more predictable? And finally, bridging the physical and social sciences gap, based on future drought study in the region, one could ask, how vulnerable is society to the projected changes in drought, and what would be needed for society to cope with them? With that, I will finish. Thank you for joining this webinar.
Okay, thank you so much, Andy. I don't know, there you are. I was going to say, if you want to join me on camera, thank you for that great presentation. So as I mentioned before, we do have some time for questions and hopefully a little bit of discussion as well. So if you would like to type your questions into the questions box, or if you want to raise your hand, we can unmute you, I believe. So, you know, Andy posed these questions here on the slide in terms of kind of some questions to consider for future drought studies in the Midwest. So one thing that we would love to hear from the audience, if you're able to share, is, you know, what type of analysis of future drought information is most useful to you and your decision making here in the Midwest. So we will take general questions about the presentation, and also if you have a comment on the future analysis, we definitely welcome those as well. Let's see here. Let me see if we already have some. I believe, Andy, you have been answering some of the questions as we've gone along. Are there any of those you want to address before we get into other questions?
Well, they're coming in fast and furious now, so I'm trying to keep up with them a little bit.
Yes.
Andrew Rose asked a question. Looks like weather in the East Coast, Southeast could be the reason for the seasonal directional flows. Have you looked at that? We haven't looked at that specifically, but I think it's an interesting question, and it goes back to the portion of the talk where we're looking at the atmospheric waves that are related to drought and how they have a wide-ranging effect on the region. So everything in some ways is related, and I think that's a really that's a good question and something that we should look into. So thank you for the question.
Okay, it looks like we have another question here. As we see higher heat out west and the overall increase in water vapor throughout the atmosphere, are we expecting to see a notable shift in the Midwest Ohio River Valley precipitation totals annually, and therefore increased flooding events in the Ohio River Valley?
Yeah, $1 million question right there. That's the central question really for U.S. hydroclimate. Is in the West we've seen this drying effect, and in the central U.S. has seen this wetting. Is that the symptom of climate change, or is the symptom of climate change a little bit more muted? Doug Cluck had made the comment before about, hey, maybe it's a single year within those decades that you're looking at that's actually causing for this so-called wetting trend. That could be part of it too. So there's a lot to disentangle, and a lot of interesting questions for us. And yes, thank you, Sunny. You hit on the central question about U.S. hydroclimate.
Yes, the $1 million question. Okay, another question here. The prediction for the future is that the increased precipitation is now a band southwest to northeast. I want to know if this increased moisture in the atmosphere over the Gulf is driving the band.
Yeah, and some other research that we're doing that's relevant to the region, what has happened, at least during our observed history, is we've really had just anomalous southerly flow. So there is that effect that is coming from the Gulf. Part of it is the atmospheric circulation setting that up. Part of it is like the thermodynamic effect of that whole process. But it does look like that there is increased moisture flux coming into the central United States that is causing that. Now, the finer details of that will need to be sorted out, and also how that changes in a changing climate as well, whether that is climate change, the symptom of climate change, or just something that was natural to the Earth system that just happened and we're going in a different direction.
Right, I want to make sure there's, it doesn't look like there's some echo here. Andy, do you see the next question? I feel like the echo might be because of us, so if you want to go ahead and read it and answer it. Sorry.
Sure. This is from Highland Wang. It is no doubt that the Midwest region has been and will be affected by anthropogenic global warming. What do you think about the roles of natural decadal and multi-decadal variability in modulating the decadal variations? And then the question gets cut off. Modulating decadal variations of drought. Well, that's interesting about that. It's how you define the PDO, what processes are then feeding into the PDO, number one. And then number two, what is the AMO? You know, there's been some recent researches that come out saying, well, the AMO is just kind of a symptom of like aerosol forcing. So, you know, disentangling what creates the AMO, why it's there in a changing climate is important to the Midwestern US drought question. Yeah, so thank you for that. It's very complicated. Molly, do you want me to keep reading questions and answering them, or do you want to jump in?
Yeah, no, go ahead. You can go ahead and do that. Yep.
Okay, so this is from Doug Cluck. It would be worth an attribution study to determine the shift toward wetting would be persistent or not. How would such a study be done? Well, we actually have a related project on this. It's more for the Missouri Basin, and Doug, you and I kind of talked about this a little bit more. It's basically constructing a study where you would take climate model simulations and try to reconcile the observed climate as we had it over the 20th and 21st centuries and see how it fit into those ensembles of simulations to try to attribute what the risk of this, what the likelihood of this was, and how it projects forward. And that's something that we're giving consideration to as part of an add-on to the study that you guys just saw. And Doug asks, and warmer Gulf Ocean waters. Well, yeah, the warmer Gulf Ocean waters, that makes a difference. There is that hypothesis there that moisture from the Gulf is feeding into the Midwestern United States and thus causing for increases in precipitation. So that's part of those larger processes that are important to the region. Andrew Rose writes, have you overlaid these maps over the aquifers? And no, I haven't. I think it was at the AMS meeting last week, or was it the AGU meeting in the prior month, where I did see a presentation on aquifers in the Midwestern United States. It was really neat, but we did not consider aquifers here in this study. It could have been your presentation, Andrew, and if it was, send me an offline email. I'd like to learn a little bit more. The next question is from Ray Wolfe, and Ray asks, can the drought duration be expressed as a cumulative distribution so we can answer the questions, what percent of droughts last 1 year? Yes, that's something that we could do based on the collection of events that we have from our integrated drought index, and that's something that could be done. So emailing me and perhaps including Doug and Molly would be nice, because I think those folks would be interested in this as well. Christopher asks, any plans to apply your methods to CMIP6 models and how your results compare to the analysis of 1916 to 2015 in their projections? Yes. Actually, that's a big part of where we're going forward. So thank you for the foreshadowing. And yes, we're going to go ahead and do that. Jeannette asks, it would be interesting to see the data portrayed against land use and land use change. That's a great question. The land surface models that we use don't have the sort of land use and land use changes that are realistic in our 20th century and 21st century climate. Including more realistic models that have that would be really nice. It's just unfortunate that those models have not been run back for the last 100 or so years for us to be able to put, say, the last 30 or 50 into a historical context. So it's a very good question. Doug Cluck asks, the challenge in the plains, of course, is the lack of practically any predictability beyond a week or two. That seems to be a major issue for longer-term climate change aspects. Well, the lack of predictability affects many different timescales, whether it's what's going to happen 2 weeks hence or a month hence or 3 months hence. And yeah, it would be fantastic that if we had some better models. We don't have those quite now. We don't have those long lead predictions, and that's a good observation, Doug. Sunny asks, overall, has there been an increase in the severity of storms, perhaps deeper low centers across the region and necessarily more severe storms, but each storm is becoming more severe than a historical norm? which would be a player in the sudden downpour events, and we may be seeing a general increase. Over the region, there has been an increase in extreme precipitation events, and that's probably related to that. We didn't specifically look at that in this study, principally because we were looking more at longer-term timescales and how the general trend in the integrated drought index was changing through time. But it is a related question, of course, feeds into that monthly to seasonal to decadal perspective that we looked at, because everything is related across time scale. So that is an important consideration about how the statistics of heavy precipitation are changing, what's driving them, and then how that's feeding into longer term changes in the region's climate. That was the final question that I see here.
Yes, thank you. And thank you for all of the fantastic questions. There was a question earlier about if we're going to be making this information, all the chat box, the questions, and recording and all of that available. And we will send out an email with the recording after. And if there is interest in record of the chat box and the questions, we can certainly do that as well. And I did put in the chat box there, you know, if you do have specific thoughts on future drought information that you'd like to see analyzed, you know, definitely let us know, as that's where Andy is taking this next, as he just mentioned, using the CMIP6 model. So if there are specifics, let us know. Once you close out the webinar, there will be a survey that pops up, and I believe that I added a spot in there to sort of to put some of that information. If you are interested in making a thumbs up for a certain type of information, you can put that in the survey. Or if you would like to chat them in the box now, it looks like, are there other ones coming in? Andy, do you want to go ahead and
Yeah, well, Doug commented on the lack of predictability other than ENSO, and that's a good point. I think where we're going right now is trying to diagnose the characteristics and behaviors of those atmospheric waves that are driving drought that we did see coming from the study, and what are some more nuanced approaches about actually understanding those waves and how to potentially predict them at some points in the future. So all hope is not lost. You know, we're doing our best, and hopefully going to drive the ball forward. Did you look at temps and ENSO connections? Yeah, temperatures have a pretty strong relationship as well as precipitation does with ENSO, and it's pretty well noted. We didn't look at temperatures specifically. We just related ENSO to the integrated drought index because that just brings together all the effect of temperature and precipitation. But yeah, there is an effect of ENSO on temperatures. And one more thing, keep the questions coming if you have them. If folks would like to see the paper that this was based on, please just send me a personal email and I can send that to you. I won't be violating any sort of copyright violations because the AMS does allow for that. And the same goes for the presentation that was given today. Please include Molly, myself, Adam Lang, who's on here too, so we can address that.
Okay, great. And I did just put our email addresses in the chat box there, if people do have questions. I don't see anything else coming in right now, and no, yeah, there's another one, Doug. Let's see, just a comment, it looks like. So there have been relatively dry years that are cool, thus impacts much less than expected. Yes.
Yeah, that's a great question. You know, there are cool droughts, there are warm droughts, and there are cool droughts, and you see this all areas of the world where you just have there's a lot of nuance here. A drought doesn't have to be warm to be a drought, and likewise, it doesn't have to be cold to be a drought. So yeah, there's a lot of nuances to different droughts and their characteristics. And
I see another.
Asks, yeah, he goes.
Go ahead.
Using OISST rather than ERSST help with the temporal resolution. Yeah, OISST is a really good product, and I tend to use it in the period that it's available. OISST came online in the early 1980s, and thus we weren't able to use it for this study because our study went back to 1916. But yeah, your point is well taken in the sense that, yeah, OISST gives you a lot more temporal and spatial resolution than an ERSST would. And another question here is from Sunny. As we see tropical weather start to move further inland than normal and dump tropical moisture further inland than normal and higher into the mid-latitudes, would there be prolonged impacts from tropical, and it's getting cut off here, more higher impacts. I'm sorry, this is an issue with GoToMeeting where I can't actually see what you're writing.
I can see the whole question. Let me just read that here. So as we see tropical weather start to move further inland than normal, the dump of tropical moisture further inland, and higher into the mid-latitudes, sorry, there was a double comment there. Would there be prolonged impacts from the tropical air mass or more short-term impact?
Well, yeah, the question has a lot of different layers to it. So the first one being, okay, you have a big dump of moisture. When it comes to like its memory in the land surface, how long would it last? And then you have to consider, all right, how much of that moisture gets sucked into the land surface and increases the soil moisture, and then how much of it just sort of runs off and is lost just because of the intensity of the precipitation. So there's a lot of complexity there in terms of that. And yeah, your question is very relevant here because there has been, or at least in the last few years, this emergence of tropical cyclones that have made their way into the region and really dumped a lot of precipitation. And I think Doug really hit that, Doug Cluck hit that in 2012, where during the summertime, there was a tropical cyclone that did go through the region and helped to really dent the 2012 drought, especially over the Ohio Valley region.
Okay, we are running up here at the top of the hour. So I think without any other questions, we'll go ahead and wrap things up. Thank you so much, Andy, for the great presentation and answering all the questions, and really thank you to everyone who attended today. I just wanted to remind you that we did just develop two pagers based on some of this research. I think we still have another one or two to come, but these might be useful for you to share if you're interested. Oops, that is two links closely together. Sorry about that, but there are two links there. And so those are available on drought.gov. So thank you again so much. When this concludes, you will see a survey pop up, as I mentioned. So that would be great if you could provide some feedback and help us improve future webinars and also this research. And we will be in contact with an email with the recording and other information. So thank you so much, everyone. And stay safe out there in the winter storm, and hopefully you can enjoy some of the snow. Bye.